So getting started with this, we have the problem says a precast concrete box girder has the cross section with the dimensions shown in feet, and then it says determine the y and z coordinates of the centroid of the cross section with reference point to O using the coordinate system shown. And so the coordinate system shown, it might be a little hard for you guys to see there. Basically, they put a z here and a y here. There's really no meaning behind that other than they probably just want to trick you a little bit, make sure you're paying attention. But otherwise, we're talking about centroids today. And so there's a process with going with centroids and how to calculate them for an entire system. They're not really that difficult, so this might be a little quick. But ultimately, we're going to kind of run through the process of what to do. So the first thing that you should do when doing centroids is you should split off the entire shape into shapes that you know. Because looking at this shape here, it's this weird kind of T-looking box girder that we don't really know what the centroid is of it. But if we take a closer look, we can see that we could split it off into rectangles and maybe triangles. And we should know, off the top of our heads, the centroids of rectangles and triangles. So I'm going to go ahead and split this off into a few different shapes that I thought would be easier. So if we look, this is probably the hardest shape to determine right here with these weird little slanted sides here. So I'm going to go ahead and take these slanted sides and find where they meet the end and just turn them into their own triangles. Okay, and then the next thing I'm going to do is this top rectangle here, we see that it meets this bottom rectangle. I'm just going to split the two off. So we've got this top rectangle going the entire length or width of the beam, and then we've got these other rectangles down here. And then I can't really draw it well, but essentially we're going to have this big rectangle that encompasses the entire cross section, and then we're going to have this smaller rectangle here, this empty space. So I'm going to go ahead and label the shapes here. I labeled this really long rectangle here 1, this all-encompassing rectangle here as 2, and then I labeled the triangles 3 and 4, and lastly I named this empty space 5. And I did that just so it would be on the bottom of our table. So now that we've split off the different shapes, this is where you want to get into your table. You don't necessarily have to create a table, but the more complex these shapes get, the easier it gets, and the more organized you are if you do have a table. So I suggest, even if it's only 2 or 3 shapes, just making a table anyway so you can go back and reference everything. So I'm going to go ahead and draw a really big table here. We're going to have our shapes, and then this is where we kind of need to know what exactly we're looking for. So essentially, to find the centroid of the entire thing, the formula that we're going to use is going to be something along the lines of, I'm going to do it in terms of YC. So YC is going to be equal to the sum of YC for each individual shape times the area for each individual shape, and then divide that all by the sum of the area overall. And so using that, we can also see that it'd be the same for Z. So we could take the sum of the Z, center of C's, divided by the sum of the A's. And these are everything that we need to find. So essentially what we need to find is we need to find YC and A and ZC. And then we can find out what these are multiplied as well. So in our table, I'm going to go ahead and write down all of our shapes. 1, 2, 3, 4, and 5. I'm going to go ahead and split them off. And then the next things that we're going to have. So I'm going to go ahead and write in YC. That's probably one of the first things that we can find. And then ZC, the center of mass in relation to Z. And then we'll also have the area. And then we're going to have these multiplied together. So YC times A and ZC times A. And that should be everything that we need there. It would be kind of helpful if maybe you wrote in the units, because everything here is shown in feet. So you go ahead and just put in feet for the distances here. It'd be feet squared for the area. And then this is a distance times area, so it'd be feet cubed. And same for this. And hopefully the units here make sense, because overall what we're going to be doing is dividing YC times A over A. And so YC times A is feet cubed. You divide that by the feet squared of area, and you get feet. So that should be what your centroid is. And so this is where we need to put in a little bit more of our knowledge about where centroids are. So we're looking at YC, which is essentially the center of area for each of these shapes in relation to Y right here. And so we're going to be using Z as our baseline, which gets kind of confusing, but essentially we're just looking for the distance Y that it is from whatever Y is 0 here. And so since this line is right down the center, a lot of our shapes happen to have centroids right down the center too. So for shape 1, this really long rectangle all along here, it turns out that its centroid would be right here on the center where Z is going to be. And so that means that YC is going to end up being 0 because it's 0 distance away from this axis here. Similar thing for shape 2, this big rectangle here, its centroid is going to end up being right on Z as well. And then I'm going to go ahead and skip down. This smaller rectangle 5 here too also happens to be have a centroid right on the center. And so we can write that as 0. And so here's where we need to look at the centroids for these triangles here that we drew. So if we look at triangle 3, one thing that we know, and hopefully you remember from distributed loads, is that the centroid of the triangle is actually going to be 1/3 away from its, I guess, fattest end here. So we've got 12 feet here, and if we take 12 feet here, we want to go in 1/3 of that 12 feet, which happens to be 4, and then we go all the way up here, and that's where our centroid of this triangle happens to be. And so we're not done yet. We can't just put 4 into our table here. We need to find out what it is in relation to this axis here. So in relation to this axis here, if we look down here, this axis happens to be right in the middle of this 9-foot dimension right here. And so that means that from the middle to the end here, we've got 4.5. And then we've got 1.5 right here. And then we've got 4 down there. And so 4.5 plus 1.5 gives us 6. And then plus 4 is 10. But this also happens to be in the negative direction because Y is pointing positive here. So this is going to be negative 10 for the Y centroid of triangle 3, or shape 3. And then similar thing for the triangle 4 over here. It's also 12 feet in length, and we go 4 feet over, which is 1/3 of it. And that'll bring us to our centroid right there. And again, there's another 4.5 on this side because this was 9, we split it in half. 4.5 and then 1.5 makes 6, and another 4 makes positive 10. And so we've got all that. Now we can look at our centroids in relation to Z. And so this is where it gets maybe a little more, there's a lot more parts to it. There's less things that equal 0. So we're going to go ahead and take a look at our long rectangle here again. And so our long rectangle here, we see the side dimension here as 1. The centroid of the rectangle is going to end up being halfway between this one. So it's going to be halfway up, which means that it's going to be 0.5 from the bottom to the middle there, all the way over to this centroid here. And then the axis that we're taking it down to is this y-axis down here. And so we're going to add up all these dimensions up until we get to this centroid here. So we've got 1.5 plus 5 is 6.5, plus 5 again should give us an 8, and then plus 0.5 is 8.5. Does anybody have any questions so far? No? Okay. So we've got 8.5 for the Z here. Next, we're going to take a look at our shape 2. And our shape 2, as the dimensions giving, it's got the 1.5, the 5, and the 1.5, which this overall makes 8. And so we want to go halfway of the 8, which means it goes up 4. So our centroid here is going to be 4 from the bottom. And then we can look at shape 3. and even shape 4 of our triangles here. And so if we look at these, we're going to end up having, again, looking at them, they should be about 1/3, or my bad, yeah, 1/3 from the end. And so if we take a look at this, this is 1.5 over here. And to find our centroid, if we take it 1/3, it should be 1/3 from this base up here, which means that we end up going a distance up 1 over here. So we end up having a 1.5 plus 5 and then plus 1, and that should give us about 7.5. And then it ends up being the same thing. I was looking at 4 over here, but 3 and 4 are in the same length, they're in the same height and position, so it's going to end up being 7.5 for that as well. And then shape 5 down here, its centroid, we have 5 over here, so we split the 5 in half is going to give us 2.5. And then we take that total distance from the bottom, it's going to be 2.5 plus 1.5, which is going to give us 4. And so those are our locations of the centroids for each of the points individually. Now we can go ahead and find the areas of all the shapes. And so the area for this rectangle here, the entire length of this is going to be 12, and then over here is 12 as well if you add everything up, and 12. So it's going to be 36, and then its height is 1 as they gave us over here. So we've got 36 for the area of shape 1. Shape 2 is going to end up being 8 times 12, which is going to be 96. Shape 3 and shape 4 are going to end up having the same areas. So we've got 1.5 as the height as they gave us. 12 is the length. And then we divide that all by 2 because it's a triangle. And so we end up getting an area of 9 there. And then same thing for shape 4. I'm going to go ahead and write it in anyway. There's 9. And then shape 5. Here we have the dimension on the right given as 5, and then the width given as 9. So 5 times 9 is 45. But we can't just leave it as 45 because this is empty space. So we want to make sure we make that a negative 45. And the reason for that is we already took into account the whole area with shape 2 here, which is this entire rectangle, and that included this area here. So we want to go ahead and subtract this from the overall area because we already included it. And so this is where we have to go through and multiply all of these out. And so if we take a look at YC times A, if we find from the YC we found for shape 1 in the area, we end up getting 0 for that. And then same for shape 2 is 0. And then right here we've got, let's see here, negative 10 times 9. I think I might have done this wrong in my work. Negative 10 times 9. Nope, I did it right. I was just looking at the wrong thing. So there's negative 90 here, and then 10 times 9 is going to be a positive 90. And then down below here, it's again going to be 0. And then we'll go ahead and multiply out ZC times the area. So 8.5 times 36, we end up getting 306. 4 times 90, or 8.5 times 36. 4 times 96 is 384. 7.5 times 9. When I did this first, I did calculate it wrong, so I'm going to go ahead and calculate it real quickly for you guys right here. So we've got 7.5 times 9 is going to give us 67.5. And this is also going to be 67.5. And then lastly, we've got 4 times negative 45, which is negative 180. Oops, I'm sorry, you guys can't see that. Zoom out of that. So that's our table for all of the individual aspects. And so now this is where we have to look again at our formulas that we have before here. And then we have to find out everything that we need to put into our formula. So I'm going to go ahead and draw a line down here and have separating lines here. And this line down here, this row, is going to be the sum of everything. And so everything we need to find. Because up here, as we can see, we need the sum of the centroids of y multiplied by the area and divide that by the sum of the area. So that means that out of all of our columns, we need to sum the areas, and then we need to sum what these centroids are here in order to find our overall centroids. And so summing the area, we get 105 for the sum of the area. The sum of this ends up being 0 for YC because these are all zeros, and then negative 90 and 90. And then we can sum together the centroids in relation to Z times A. So we've got 306 plus 384 plus 67.5 and another 67.5 and then minus 180. And that gives us 645. And so we can go ahead and take a look down here. YC overall is going to end up being whatever this value is here, which is 0, divided by 105, which is the area. And it's going to end up being 0. And then ZC, the centroid in Z, is going to be the 645 divided by the area, 105, which is going to give us 6.14 feet. And so we can go ahead and input those into the bottom here. So we've got 0 feet here and 6.14 feet there. And those are our final answers. Does anybody have any questions on how to do these? These are pretty straightforward, but I figured I'd run through one for you guys. Okay, so the question here is determine the second moment of area with respect to the x-axis passing through the centroid of the cross-section below. And so this is something that you guys cover in lecture, I think, on Monday and today. So it might be fairly new to you guys. But essentially, second moment of area, or area moment of inertia, that's something that you'll find. It's not really important right now, but when you get into dynamics and whatnot, it becomes a lot more important with how we calculate motion and everything. So right now, we're just learning how to calculate it. And it's kind of similar to how we calculated centroids, meaning that we're going to use another table to make things easier for us. But overall, you'll discuss this in lecture, and I'm just going to write it down here, is the moment of inertia is going to be equal to, first off, we have these formulas here. So if we had just this shape by itself, this rectangle here, the moment of inertias would be just these formulas that we have. But when we take it into relation of this entire shape and the x and y axes, we're trying to find the moment of inertia about these axes, meaning that we have to do some math calculations to figure out where the moment of inertia is about this axis here, because it's not going to be exactly like it is in the formula here. We need to change some things. And so we're going to go ahead writing this equation down. I'm going to write it in terms of x here, because that's what we're looking for, is with respect to the x-axis. And so area moment of inertia with respect to x here is not only, it's going to be equal to the sum of these. So sum of Ix, which is 1/12 base times height cubed, plus the sum of area dy squared. And essentially what this means is we want the sum of the area and then the distance of the centroid of this in relation to the x-axis here. And so that might not make too much sense here. If you're kind of questioning that, I would say look it over in the videos, because Mr. Hosting did those, and he does a good job explaining exactly what happens here. And so we're going to go ahead and make another table because we have more information we need. So we're going to have to find what the moment of inertia for the shapes are, and what the area for each of the shapes are, and this dy value here. So I'm going to go ahead and draw this table. First thing we need to do is split this little L shape here into two different shapes. And there's a couple ways you could go. You could draw a line and split it here and have a rectangle here and one here. Or you could split it here. And this is the way I did it, was you have this rectangle on top and this other rectangle on bottom here. And I'm going to go ahead and draw the dimensions out for these. And so the dimension of this rectangle here, we've got 6.5, And then 6.5 plus 3.5 gave us 10, but we're going to subtract this 1 inch. So we have 9 inches over here. And then, which means that its centroid is going to be, from the bottom, 4.5 inches, which will come in handy later. And then up at the top here, 4.5 and 1.5. I'm just going to draw out the whole dimension again. That's going to give us 6 inches. And then its centroid from the end over here is going to be 3 inches. Okay, so we've got that. And we can label these as shape 1 and shape 2. Or we could just draw them off to the side. We've got 1 and 6. And we've got 1 and 9. And then last but not least, we need the table. Oh my gosh, I'm so sorry. I'll zoom out here so you guys can see more of what I'm doing. And then we'll have the sum over here. And so a few things that we need to look for. First thing we can look for that's really easy is the area. And then next thing we want to look for is dy, which since we're going to be squaring dy anyway, I'm going to just go ahead and write the absolute value of dy. It doesn't really matter if it's positive or negative like we had to find in the centroid problem, so just that. And then we're going to have a column for a area times dy squared. And then last but not least, we're going to have the moment area moment of inertia here. And we can go ahead and write in our units again. So the area is going to be in inches squared, because everything's in inches, we square it. dy is going to end up being in inches because it's just a distance. And so here we have area times dy squared. That's going to be inches squared times inches squared. We're going to have inches to the 4th. And then area moment of inertia is also going to be inches to the 4th, which you can see here in this equation. We've got base times height cubed. That's going to end up being 4 dimensions multiplied together, or inches to the 4th. And so that's what we have here. We can go ahead and get started with finding the area. So for the area for this one here, it's 1 times 6. And we end up having 6 inches squared for that one. The area for this one is 1 times 9. We end up having 9 for that one. And then dy, this is where it does get a little bit confusing again. And so dy is essentially the distance from this x-axis here, because they gave this as the x-axis and this as the y-axis. And so dy is going to be this, the distance from this x-axis wherever these centroids are. So for our shape 1 here, this 6 by 1 inch shape, we can see that our centroid here, since it's 1 inch here and it's a rectangle, our centroid is going to end up being 0.5 inches from the bottom and from the top of that shape. And so we have x here. We end up finding, to find this, we can go up the 3.5 inches all the way to the top of this rectangle. And then we know that it's 0.5, or just whatever is the middle of this rectangle. So we go up the 3.5 inches and go back down 0.5 inches, and that means our dy ends up being 3 inches. Are there any questions about that? Okay. And we could do something similar for our value here. And so we have the x-axis here for shape 2. For shape 2, we see that it's 4.5 up here. So what we can do is x-axis to the very bottom is 6.5 inches. So we could take that and then subtract away the 4.5 here. And 6 minus 4.5, that should give us a value of 2. And so now we know these, we can go ahead and calculate what our area times our distance from the y squared is. So that's going to end up being 6 times 9, or 6 times 3 squared. We're going to get 54. And then this is going to end up being 9 times 2 squared, which is 36. And then we're going to have to go ahead and sum these. So I'm going to go ahead and add these together. We're going to get 90 when we sum these together here. And then next, we're going to go find the second moment of area using the formula here. And so the formula is 1/12. And then for x, they give us that base is the bottom one, or the one that's parallel to the x-axis, and then height is the one that's perpendicular to the x-axis. And so 1/12, using that, we can look at our shape here. This is 6 inches in total, so 6 is going to be our base, and then our height is the 1 inch, and so 1 inch cubed, we're going to end up having 0.5. And the next thing we're going to look at is for this shape here, it's going to be 1/12. Our base here is 1 inch, and our height is 9 inches. We take the 9 cubed, and we end up finding this whole thing divided by 12 is 60.75. And we'll go ahead and sum this together now, and we get 61.25. And then last but not least, we need to go ahead and add everything together. So as I wrote previously here, Ix is equal to the sum of the area moment of inertias multiplied by area, or the sum of area times the distance from y squared. And we have those down here, so we can go ahead and write Ix is equal to 90 plus 61.25, or 151.25 inches to the fourth. And we can go ahead and report that in our answer box here, 151.25 inches to the fourth. Does anybody have any questions about this now? No? Okay. I'll go ahead. Here we have the question, determine the distance YC, this one here, that defines the location of the centroid. And it says the distance from the bottom surface of the beam to the x-axis shown. And so might get a little confusing. I'm going to go ahead and write this out as x prime maybe over off to the side here, just because we're going to be using this axis later on. The next questions that we have are determine the second moment of area about the x-axis shown. So this axis here, located at the centroid. And then determine the second moment of area about the y-axis shown, located at the centroid. And the centroid of this beam, because it's symmetrical, that's one thing that by inspection, if you have a shape like this and you see that it's symmetrical, and they say this is located at the centroid, you should be able to see that it's just right down the center of it. We kind of ran into that earlier when we looked at this problem. We found the centroid was just right down the center here, so all these YC's just happen to be 0 because they were located on that axis. And so the centroid of this overall shape will be right down the center. So we'll go ahead and take a look at that. We'll have part A here. Again, we'll make another table. Before we make a table, we're going to go ahead and split this off into different shapes. So again, for this top rectangle here, we've got shape 1, and we've got shape 2, and shape 3 lastly. That's how I labeled them. That's kind of what makes the most sense here. And so we're going to go ahead and split this off into multiple parts of the table. And so we've got our shapes in this first column here. So we've got 1, 2, and 3. And then we've also got the sum of everything down below. And so for here, again, we're finding the centroid, or YC here, the centroid in X, or in relation to this X here. And that's going to be using our formula like this, where it's YC is equal to the sum of YCA divided by the sum of A. So this is the centroid of each individual shape multiplied by its area, and then we sum all those together, and then we divide that by the sum of all the areas together. And so looking at our thing here, our table here, we can go ahead and have YC, which is given in meters this time. We're going to have area, which is given in meters squared. And then we're going to have YC times area, which is meters cubed. The units there. And so we can go ahead and take a look at all of our shapes here. So the centroid of this shape here, this rectangle, is halfway between the height here. So 0.2, it's going to end up being 0.1 from the bottom, or from the top here. But anyway, it's going to be right in the middle of that. So we can go ahead and add this. We want the total distance from the very bottom of this, or x prime as I labeled it. So we'll go ahead and have 0.2 plus 0.6 gives us 0.8. And then we'll add the 0.1 here. We end up getting a YC of 0.9. Next, we're going to take a look at this shape 2 here. It's again going to be right in the middle, or from the bottom of the shape, it's going to be 0.3. And so we can go ahead and take the 0.2 plus the 0.3, we get 0.5. And then lastly, for shape 3, it's going to be right in the middle, which is 0.1 up, and that's its exact distance from the bottom, so 0.1. And then we've got that information. Now we can find the areas. So for shape 1, we've got 0.2 and 0.8. 0.2, 0.8, which gives us 0.16 total. For shape 2, we've got 0.2 and 0.6, which gives us 0.12 total. And then shape 3, it's again 0.6 as the base, 0.2 is the height, and that gives us 0.12 again. And we can go ahead, we're going to need the sum of the areas anyway, so we can go ahead and sum them all now. And we get a total sum of 0.4 meters. And then we'll go ahead and move on to YC times A. We're just going to go through and multiply these together and put them in this column here. So 0.9 times 0.16, we get 0.144. 0.5 times 0.12, we get 0.06. And then 0.1 times 0.12 is 0.012. And we'll go ahead and add all of these together. We're going to get 0.216. And so following this formula here, we're going to find out that our YC is going to be equal to 0.216 meters cubed divided by 0.4 meters squared, or overall 0.54 meters from the bottom. And so I'm going to go ahead and write this out here, 0.54 meters. And so our distance from the bottom to where this x-axis should be located is 0.54. And so that's our part A right there. That's what we needed for part A. And so part B is asking for the second moment of area about the x-axis and about the y-axis. And so this is where we need, again, take a look at what I wrote out earlier, which is that these formulas here, Ix, or the area moment of inertia, is going to end up being equal to the sum of all of the area moment of inertias in each of these three shapes, plus the sum of the area times dy squared for this one. And then area moment y is going to be the sum of Iy plus the sum of the area dx squared. And again, these dy and dx just means the distance from these axes here. And it does get a little confusing. I'm pretty sure this is how it's supposed to go. The distance from this axis is supposed to determine what this is. It seems kind of backwards of what it is, but just know that, let's say we're finding the second moment of area x, we're just finding the distance dy, the distance from x, because the further out it is from x, the more inertia it's going to have. So that's why we're finding this dy here, is we're essentially, you can think of it as the distance from x. And so we'll go ahead and write out our table again. This one's going to be a bigger table. And to draw it out, I'm just going to go ahead and take the entire length. And so we're going to have 1, 2, 3, and then down below the sums. And so for this, we're going to go ahead and have the area and then dx, or the distance from x, and I'm going to go ahead and label this as dy actually. We'll do that first, dy, and then dx, and then we're going to have a dy squared and a dx squared, and then lastly ix and iy. It's kind of a mouthful. Again, for the dy and dx, it doesn't really matter which direction it is because we're going to end up squaring them. So I'm just going to go ahead and write in the absolute values just so we know that it's always going to be positive. And so we can go ahead and copy over our areas from before. So we've got 0.16 0.12, and 0.12. And so, let me make sure I did this right. So our dy's here, let me just check over my work, what I have. So our dy's are going to be our distances from our x-axis here. And so if we're looking for shape 1, the dy is going to end up being this centroid from this x here, whatever this distance is here. And so to find that, we're going to essentially have, as we found before, the distance from the bottom of this shape all the way to this centroid is 0.9. And we're going to subtract this 0.54 from it. So 0.9 minus 0.54 is equal to 0.36. And actually, since we already have the centroids here, what we're essentially doing is we're taking the absolute value of our centroid, subtracted, or minus this value here, 0.54. Because we already found the centroid in relations to the bottom, and so we just take our centroid relation to the bottom and subtract this height here to get whatever this distance is here. And so the absolute value of that, we end up getting 0.04. And then lastly, you have 0.1 minus 0.54, and we get 0.44. Okay, and then dx, it's going to be the distance from this y-axis here. But like I was saying, all the centroids of these shapes are going to end up being on this y-axis, so all of the values are going to be 0 because there is no distance away from this y-axis here. And so it's going to be 0, 0, and 0. And then this is where we go ahead and multiply these out. So the area times dy squared, we're going to end up having 0.16 times 0.36. I wrote down below, or before, as 0.0576. 0.12 times 0.04 is 0.0048. And then 0.12 times 0.44, 0.0528. And we'll go ahead and sum these all together. We do that, we get 0.1152. And then a dx squared, these are all just going to end up being 0 as well, just because all of the dx's are 0. There's really no difference from the center of this axis here. Next, we can calculate our ix's and our iy's. And so ix is going to be, ix is 1/12 base times height cubed. And so we're going to go ahead and write these all out. 1/12 times, for our shape here, shape 1, we've got 0.8 as the base and 0.2 as the height. 8. Let's see. Let me make sure I did this correctly. I think I might have written it in backwards in my work here, but this should be the correct way, because our total base is 0.8 and then our height is 0.2. Let's see. Wait, could you repeat?
Never mind. I was reading it as the distance to the center.
Oh, yeah. That's what we've got before here. So our moment of inertia, just our 0.8 and our height, just the shape by itself here. It's going to be 0.8 times 0.2 cubed. We end up getting a really small value of 0.000533. And then our next one, for this shape here, the base is instead going to be 0.2, and the height is going to be the 0.6 cubed. And so when we calculate that all together, we get 0.0036. And then, let's see, lastly, we've got our base is 0.6 down here, and our height is 0.2. So 0.6 times 0.2 cubed, we get 0.0004. And we sum all of those together, We get 0.004533. And then moving on, we can find out our y's here. Essentially with the y's, it's going to be the same dimensions. We're just going to flip them around, because instead of base times height cubed, it's going to be height times base cubed. So 1/12 of 0.2, 0.8 cubed, and we're going to get 0.008533. 1/12 of 0.6, 0.2 cubed, we're going to get 0.0004, and then 1/12, 0.2, 0.6 cubed, we're going to get 0.0036. We go ahead and sum all of these together, and we get 0.01253. And those should be the sums of all of that. We're going to go ahead and follow through with our formulas that we wrote here before. So the moment of inertia, or second moment of area, about the x-axis, Ix here as we have below, is going to be the sum of all of these values plus all of these values here. So that's going to be equal to 0.004533 plus 0.1152. And so we add those together, and we end up getting a value of 0.1197 inches to the fourth. And that's our Ix. And then we end up getting, for Iy, is going to be just this value because a times dx squared is 0. So it's going to be 0.01253 inches to the fourth. And that should be everything that we were asked for this question here. So does anybody have any questions about that? What was that?
Shouldn't it be meters to the fourth? Oh, wait.
Yeah, you were right. You were right. It is meters to the fourth because they gave us all in meters. Yeah. So meters to the fourth. Yeah, my bad. Thank you. Any other questions or anything about this?
Are these equations going to be on that equation sheet?
That's a good question. I don't have my equation sheets with me. Tell you what, I'll look and see if it is on the equation sheet. A lot of times in the question, if they ask you for like the moment of inertias, they'll usually give you, like on this problem here that we ran through, they showed you a rectangle and they gave you what it is for each one. But I would definitely know what it is for rectangle anyway, just memorize that. If it usually gets another weird shape like a circle or a triangle or something, they'll usually give that to you. But still, it wouldn't hurt to review. I'm going to check over my equation sheet. Hopefully in my equation sheet, I'm pretty sure they told you this whole equation here, but I'm not entirely certain about that. So I'm going to take a look and make sure they have that. But as far as these equations here, I would study it for a rectangle, but any other shapes, they should just give it to you. So any other questions about that? Okay, that's all I have for you guys today.